Hello, everyone. Today we're going to talk about fractional factorial experiments at two levels. Okay, this part of the materials is from chapter 5 of this book, Experiments, Planning, Analysis, and Parameter Design Optimization by Jeff Wu and Michael Hamada. Okay, let's look at the outline. First, we're going to have a look at the case study, leaf spring experiment. And that is the section 5.1 in this book. And then we're going to talk about effect aliasing resolution, minimal aberration criteria. After that, we're going to talk about the analysis of fractional factorials and techniques for resolving ambiguity in Alias effects. And in the end, we're going to talk about the choice of designs, use of design tables for fractional factorial design. And in the end, we're going to talk about blocking in 2K-P designs. Now let's look at this experiment. So the response variable y is the free height of a spring. Spring is just a spring, and you press it, it will be resilient and then come back to the original height. So the target is 8 inch. The free height is 8 inch. We want to get y as close to 8 as possible. This is a nominal, the best problem. So 5 factors at 2 levels. So those are the 5 factors: heat temperature, heating time, okay, transfer time, hold down time, and quench oil's temperature. They have 2 levels. Each factor has 2 levels. And we use -1, +1 denote these 2 levels. Okay, we have 5 factors. If we are going to do a full factorial design, it will be 2 power 5. Okay, 32. But now we only use 16 run design with 3 replicates for each run. So this will be a 2 power 5 - 1 design. So this is a 2 power 5, it's a full factorial design. And then 2 - 1 is the 1/2 fraction of the 2 power 5 design. So this is called fractional factorial design. We're not going to do the full factorial. Only use the fraction of the full factorial design. So this is a design matrix. We're going to use B, C, D, E, Q. Those are the 5 factors over here. We're going to set them into minus plus levels. So we're going to, so here we have 16 runs. For each run, we're going to do 3 replicates. And then based on those y values, yi, this is, we're going to calculate the mean of this row, variance, sample variance of this row. And then we're taking the log of the variance. Okay. Now, so this will be our response variable. This will be our target. This log will be our dispersion of variance. So we want to get in the height to be as close as possible, to as close to 8.0 as possible. So, but there, and also we want to minimize the dispersion, minimize the variance. So if we are going to use a full factorial design, then there will be 31 degrees of freedom. It will be allocated as follows because we have 5 factors, so 5 main effects. And then we have 2 factor interaction, and a 3 factor interaction, and a 4 factor interaction, and then 5 factor interaction. So those will be 5, 10, 10, 5, 30, 31. So the total we have 31 degrees of freedoms. But if we are going to do the fractional factorial design, we have to sacrifice some of the factorial effect. So using the effect hierarchy principle, one would argue that 4 factor interaction, 5 factor interaction, those may even 3 factor interaction are not likely to be important. So this here we have 16 such effects. That's half of the total runs. So if we are going to use 2 power 5 design can be wasteful. Why we use 4 factorial? Why not just use 16 so that we can get some ideas about the main effect and the 2 factor effect at least, right? And then if you're really interested in those high order or 4 factor, 3 factor, 4 factor, 5 factor interaction, you can do more follow-up experiments. So use fractional factorial design instead of the 4 factorial design is very economic. But there's no free lunch. What price to pay is those are our price. So in the design matrix, we know that column E equals to BCD. So effect aliasing and defining relations. So what price we pay? Aliasing effect, because E equals to BCD. The effect of E is aliased with the interaction BCD. So let's have a look at the design matrix. Let's go back. So if you E equals to BCD, right? If you look at BCDQ, if you look at BCDQ, did you find any patterns? BCDQ are actually 2 power 4 full factorial design. And then you have an actual factor here. Then you use BCD, multiply them together equals to E. You see, minus, plus, plus equals to minus, plus, 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 plus. Minus, minus, plus, plus. So E is actually equals to the multiplication of BCD. So that's why E, the main effect of E is aliased with a 3-factor interaction effect of BCD. So if you multiply by E, BCD together, because this equals to this, okay? So if you multiply by E and the BCD together, it will become I, 1, 1, 1, 1, right? So I is a column of +1. It's an identity element in the group of multiplications. Note that the mathematical similarity between aliasing and confounding. So what's the difference between confounding and aliasing? Some people use confounding and aliasing interchangeably, but confounding usually refers to the aliasing effect with the blocks. But aliasing, for most of the time, is referring to the effect and the effect, factorial effect. And the factorial effect, they are aliased. So that's a main difference. And now, if we have a defining word or defining relation, that is BCDE, and you can use E equals to BCD, like you can set up a BCDQ, okay, as a 2 power 4 full factorial design, and then you use E equals to BCD, then you will be able to get 2 power minus 5 minus 1, 2 power 5 minus 1 design. So here we have 15 aliasing relations. So B equals to CDE, C equals to BDE, because these are the same relationship. You see here, from the BCDE, you can get B equals to CDE, C equals to BDE, D equals to BCE, and at the same time BC equals to DE. And if you multiply by Q on both sides, you will be able to get Q and also E. So those are all the 15 effect aliasing relations. Now, in order to discuss the clear effect, let's have a look at the definition. A main effect or 2-factor interaction effect is called clear if it's not aliased with any other main or 2 factorial effects, interaction effects. And strongly clear if it's not aliased with any main effect, 2-factor and 3-factor interaction effects. Therefore, a clear effect is estimable under the assumption that 3-factor and higher interaction, they are negligible. A strongly clear effect is estimable under the weaker assumption of negligible 4-factor and higher interactions. In the 2 power 5 minus 1 design, with these defining relations, which effects are clear and strongly clear? If we go back, if you see B, C, D, E, they are clear. Q, PQ, CQ, DQ, EQ are strongly clear. Let's go back. You see B, why B, C, D, E are clear? Because they only are elicited with 3-factor interaction, right? They are not elicited with other main effect or 2-factor interaction. But if you look at Q, Q is only elicited with 5-factor interactions. They are not elicited with 3, right? So it's not elicited with any main 2-factor interaction or 3-factor interactions. Also, same thing, same happened for BQ, CQ, DQ. So they are strongly clear. Now let's consider the alternative plan 2 power 5 minus 4 design, 2 power 4 design, 5 minus 1, with I equals to BCDEQ. So if you were given these defining relations, so you can just use BCDE to generate the full factorial design, then Q equals to BCDE, you will be able to generate the experimental plan. It is said to have resolution 5. This is resolution 5 because this defining relationship word is 5, but the length is here is 4. So this is resolution 4 design. This is resolution 5 design. It can be verified that all 5 main effects are strongly clear. Okay, all 10 2-factor interactions are clear. And you can do the derivations as what we do here. And this is a very good plan because each of the 15 degree of freedom is either clear or strongly clear. This is a better plan than what we have before, BCDE. This resolution is lower. So now let's have a look at the defining contrast subgroups for 2 power k minus p. So 2 power k is a full factorial design. Now we only run, we're going to 2 minus p, fraction of the 2 power k full factorial design. And this fraction is defined by p independent defining words. The group formed by the p words are called defining contrast subgroups. It has 2p minus 1 words plus the identity element I. So the resolution is the shortest word length among the 2 power p minus 1 words. For example, if you have a 2 power 6 minus 2 design, so you can have 1, 2, 3, 4, full factorial design, 2 power 4, right? And then the 5th factor equals to 1, 2, 6th factor equals to 1, 3, 4. Okay, those are the 2 independent defining words. That is I equals to 1, 2, 5, I equals to 1, 3, 4, 6. And here, 5 equals to 1, 2, 6 equals to 1, 3, 4. And then you have 1, 2, 3, 4 full factorial. Then use 5 equals to 1, 2, 6 equals to 1, 3, 4. And you also have the I equals to, if you multiply this together, also equals to I. So 2, 3, 4, 5, 6. So the defining contrast group is I to 1 to 5, 1, 3, because this one defines 5. 5 equals to 1, 2. This one defines 6. 6 equals to 1, 3, 4. And this is from extra one by multiplying by these 2 independent one together. So this design has resolution 3 because the word length pattern among the 2 power p, because the p is 2. 2 power 2 minus 1 is 3. So you have 3 defining words. And these 2 independent ones are here. Now, if we use this design, defining contrast subgroups, then all the 15 degree of freedoms, okay, can be identified based on the defining contrast groups. For example, I equals to this one. Now, for each one of them, you multiply by 1, right? Then you have 1 here, 1, 1 canceled, 1, 1 canceled, then 1, 2, 3, 4, 5, 6. Then you multiply by 2, multiply 3, and you multiply all of them. Then you will be able to see 3, because this one, 1, 2 is elicited with 2, 5. 1 elicited with 2, 5. So it's elicited with the 2-factor interaction effects. So it is not clear. But 3, only 3-factor interaction. And 4, 3-factor interaction. 5 is not clear because you have 1, 2 here. So by looking at this alias in groups, you can see 3, 4, 6, 2, 3, 2, 4, 2, 6, 3, 5, 4, 5, 5, 6. They are all clear. So this one has resolution 3. So if we define the word length pattern and resolutions, define AI as number of defining word of length I, you see, this only goes from A3 because the length is defining words has to be length of 3. So this one will be A3, A4, A5. Okay, but why it goes from 3, not from 2? Because if you have a defining word with length of 2, then main effect is illustrated with another main effect. So you have to go from the length pattern, the minimum length to be 3. So the resolution is the smallest r, such that AR greater than or equals to 1. That means the smallest r. So here is 3. So this is a resolution. If you have the design 1110, for example, what do we have here? This is 3, A3, you have 1 defining words, so you put a 1 here, and A4, you have 1. A5, you have 1, so you have 1110, you don't have this defining word. So the minimum defining word length is AR is 3, so the resolution is 3. So maximum resolution criteria for any fixed K and P, we choose the 2 power K minus P design with maximum resolution. So we want our resolution to be high, okay? In any resolution 4 design, the main effects are clear because it's resolution 4. Main effect is illustrated with a 3-factor interaction. Resolution 5, the main effects are strongly clear and 2-factor interactions are clear. And among the resolution 4 design with given K and P, we got to choose the largest number of clear 2-factor interaction effects. This will be the best, okay? Now, fractional factorial design is actually a projection of the full factorial. For example, if you have resolution R design, it is its projection onto any R-1 factors is a full factorial in the R-1 factor, just as what we discussed before. This would allow effects of all orders among the R-1 effects to be estimable. So caveat, it makes the assumption that other effects are inert, okay? For example, if we have a 2 power 3 minus 1, obviously we have 2 power 2 full factorial. And then you have the third factor. For example, if you have 1, 2, full factorial, 3 equals to 1, 2. And that means you're projecting the original full factorial line. It's supposed to be 2 power 3, right? But you minus 1, you can project to this screen or this screen. Why you have multiple directions? Because you can do it with 3 equals to 1, 2, or 2 equals to 1, 3, or 1 equals to 2, 3. Or you can do it with 3 equals to minus 1, 2. So there are different ways to project into the there are different ways to project the 2 power 3 design into a 2 power 2 design, okay? So now let's have a look at the minimum aberration criteria. So here is a motivating example. Consider we have 2 designs. They are all 2 power 7 minus 2. So what is the first design? This is 4, 5, 6, 4, 5, 6, 7. 1, 2, 3, 4, 6. 1, 2, 3, 5, 7. And then this is 1, 2, 3, 6, 1, 5, 4, 5, 6. And then you have this one. So for the first one, how do you do the experiments? You can do 1, 2, 3, 1, 2, 3, 4, because this is a 2 power 5, 2 power 5 full factorial design, right? And then you can do 1, 2, 3, 4, 5, a full factorial design. And then 6 equals to 1, 2, 3, 4, 7 equals to 1, 2, 3, 5. Then you will be able to get the fractional factorial design. That means the 6 equals to the previous one. They are illustrated with 1, 2, 3, 4. 7 is illustrated with 1, 2, 3, 5. But for this one, 6 is illustrated with 1, 2, 3. And 7 is illustrated with 1, 4, 5. If you look at the resolution, this one is A3 is 0, no A3, right? A4 is you have A4, A4. A4 you should have only 1, right? Then A5 you have 2. Then A6 you don't have any. So for here, A4, A3, A4, A4 you have 2. And then you have a 1, 2, 3, 4. You have an A6, you don't have an A5. So for this one, this is your word length pattern. So which one is better? Intuitively, you may argue D1 is better because this is 1, right? You only have 1 4 factorial effects, but this one you have word length is you have 2, word length is 4. So A4 D1 equals to 1, less than A4 D2 equals 2. And then based on the effect hierarchy principle, we would argue that the first design is better. So this is called minimal aberration criterion. For any 2 power k minus p design, D1 and D2, let R be the smallest integer such that AR D1 does not equals to AR D2. Then the D1 is set to be have less aberration than D2 if this one is less than this one. If there is no design with less aberration than D1 has a minimal aberration. Throughout the book, this is a major criterion used for selecting fractional factorial design. It's called the minimal aberration criteria. Now let's have a look at what the experiments that we talked about, leaf spring experiment. That is a case study. Same strategy as the 4 factorial experiments, except for the interpretation and handling of E. Because if we're going to analyze the location effect, this will be very similar to the 4 factorial experiments. But now we want to interpret and handle the illicit effect more carefully because we have some illicit effects involved in the experiments. So for the location effects, the factorial effects are given in table 3. So this is our table 3. And verily one may judge that Q, B, C, CQ, possibly E, BQ are significant. So how? Okay. Because if we look at the location, this is a location, this is a mean, right? If we look at the amplitude, which one is bigger? B, Q, B, C, CQ. It seems that B is bigger, C is bigger, Q is bigger. Anything else is bigger? CQ is bigger, right? And if you want to consider E is a little bit bigger too. E and BQ, possibly E and BQ. BQ, what is BQ? BQ is 0.085. So those amplitudes are higher. That means they, visually, you may say that they are significant. Then one can, you can also apply the test to confirm those are significant by using the statistical test. Now, if we look at the BQ and CQ interaction plot, show that they are synergistic. Okay, so if we look at the plot, oh, so those are the half normal plot. You see Q, B, C, CQ, and possibly E and BQ, they are significant based on the half normal plot. This is a visual way to judge which one are significant. If you look at the interaction plot, they are synergistic because they are all going the same way. So if we say, okay, now we identify those significant factors, then we can fit a model with the Y. Then those are the parameters we can develop the model. Now, same thing will happen for the dispersion effect. So you can use Zi equals to log S square values, then the half normal probability plot. And visually only B stands out. This is confirmed by analyzing the, using the statistic test. For illustration, we can include B, DQ, BCQ. So visually only this one is significant. This is for dispersion effect. That means we are going to use Z equals to log S square as the response variable instead of Y bar, the mean. From here, we can see B is pretty significant, but DQ, BCQ, they are also having a pretty high amplitude above 1. So for safe, for the purpose of safety, then we can include more, or a little bit more rigor, we can include B, DQ, BCQ together. Then using the data that you got, you can get this model. Now, we can use two-step procedures for optimization. First step, we want to minimize the dispersion. That means we want to minimize the variance. So if we want to minimize the variance, we choose, you see this is our model, right? We have to, this log is the monotone function. That means we want to make sure this side is as small as possible. Then XB should take -1. DQ should be taking -1 too. Then this one take +1. Then we will be able to minimize the variance. So B equals to minus. Based on the DQ plot, we choose the combination with the lowest value. So DQ should be multiplied together. It should be negative. DQ, this is a CQ. So if you plot the DQ, you will be able to see, oh, here is DQ. You see this one is more, much smaller, right? So D plus Q minus. So D plus Q minus. And then with B minus minus and C plus to attain the minimum at a BCQ plot. BCQ plot, figure 6. Oh, this one is minimal. So we want to make sure the right side of this equation to be as small as possible because we want to minimize the variance. So this will need to B minus and DQ minus and BCQ plus. In this way, we will make each of the last 3 terms negative. So this one is negative, negative, and this one is this one should be positive, right? Yes, BCQ is positive. So, but you have a negative sign here, so it's still negative. So you make it smaller. Now, step 2. Now we have already set those levels, right? And we have already set the levels of DQ, B, C, and now we need to set D, okay? And also other factors E. So you have already set D. And we need to set E so that we are as close as to 8 as possible. So we take E equals to 2.54. So in this way, we optimize our production process by first minimize the variation and then move the mean to the target. But this XE is not -1 or +1. This is way outside the experimental range for factor E. Such a value may not make physical sense. The predicted variance for this setting may be too optimistic, so not substantiated. So that means sometimes we do this kind of optimization. We need to do follow-up and check whether we are in the proper range and to move those factors. Now, technique for resolving ambiguity. Obviously, we have ambiguity, but how do you resolve ambiguity? For example, B is clear, DEQ is strongly clear. However, BCQ is illicit with DEQ. But BCQ is significant in the previous one when we use them in the modeling. But the real effect is it from BCQ or DEQ? So we can use the following 3 techniques to resolve the ambiguity. First, subject knowledge expert, okay? You can ask an expert in the factory, or you ask them, they may suggest that some effects in the alias are not likely to be significant. And also you can use effect hierarchy principle to assume away some high order effects. Or the third one is what we're going to talk about. How do you do follow-up experiments? If you couldn't solve the problem in the first one, second one, now let's do some follow-up experiments. So the follow-up experiments, one way to do it is a fold over. So let's look at this one. This is a 2 power 7 minus 4. That means 2 power 3 full factorial. You can do 1, 2, 3 full factorial. Then 4 equals to 1, 2, 5 equals to 1, 3, 6 equals to 2, 3, 7 equals to 1, 2, 3. So those are the generators. And none of its main effects are clear. Now, if we want them to be clear, how to do that? To delist them, we can choose another 8 runs with reverse design for each of the 7 factors. This follow-up design, D2 will have the generators. That means 4 equals to minus 1, 2. Okay. And 5 equals to minus 1, 3. 6 equals to minus 2, 3. And then 7 equals to 1, 2, 3. So this one is not inverse. We choose another 8 runs with reversed signs for each of the 7 factors. Okay, while with the extra degree of freedom, we can introduce a new factor as a block because you run this first and this next, and then you add another block. That means new factor 8. And for run number 1 to 8, and the minus 8 for run number 9 to 6. And then combined design is actually a 2 power 8 minus 4 because you have 8 runs and another 8 runs is 16 runs. Then in this way, all main effects are clear. You see here, this is 1, 2, 3. And here, what we are going to do is we reverse the sign. For example, 1, 2, 3, you have minus 1, minus 2, minus 3. Then 4 will equals to 1, 2. So 4 equals to 1, 2. Okay, this will be minus 4, minus 5, minus 6, minus 7. Okay. And you see, for each of the factors, we reverse the sign. Okay, but now you see this minus 7 is still equals to minus 1, minus 2, minus 3. Okay, the multiplication of these 3. And this is 7, it still equals to 1 multiplied 2 by minus 3. So this column, they are still equals to this one. Okay. Now, that's this is called fold over. Just if you have 1, 2, 3, 4, 5, 6, 7, you just add a negative signs on the original design. You have a fold over. Now, fold over version 2. Suppose you this is an entire fold over. You have 1, 2, 3, 4, 5, 6, 7. You just fold over all of them. Okay. You see the signs are all reversed. But now, suppose you want only run a fold over one factor, right? Suppose one factor is very important. We want the Alias 5 and all 2 factor interaction involve 5. So instead, we choose this follow-up design. That means 5 equals to minus 1, 3. You only then the combined D1 plus D3 will be 2 power 7 minus 3 and still resolution 3 design. But you see here, this one is resolution 4 because, but here you actually make sure 5 is delist and all the 2 factor interaction involve 5 at delist. So this is a different way to do it. This is a new generator. Since 5 does not appear in this equation, then 5 is strongly clear and all 2 factor interactions involve 5 are clear. However, other main effects are not clear. Okay. So choice between D3 and D2 and D3 depends on the priority given to the effects. The critique, some people like the fold over, some people they don't like it because fold over is not very efficient because you need to double all the runs. Sometimes when you follow up, you may only run 2 more experiments, 2 more experimental runs, not just 8, right? So in practice, after analyzing the first experiments, a set of effects will emerge, need to be delist. And usually we require much fewer runs to delist the effects. So a more efficient technique that does not have this deficiency is the optimal design. Now, this is a very interesting approach. Let's look at the optimal design. Okay, so this approach adds runs according to a particular optimal design criteria, D or DS criteria. And now we're going to discuss the optimal design criteria. It's depending on the model. So this is your model, right? Now, in general, the model should contain all effects and their alias, except the judged unimportant a priori or by the effect hierarchy principle, identified as significant in the initial experiment. For example, we think that BCQ and DEQ, they are alias, then we think we want to study these 2. Then we include both of them in the model, okay? Now, we add a block variable that account for the difference in the average value of the response over different time periods because you have already run some experiments. Now, we have new experiments coming, right? And then we have a block effect. You just add a block effect over here. And then an intercept. So this is a new model because now in table 5, the column B, C, D, E, Q comprise the design matrix, and the column B block B, C, Q, D, E, Q, DQ comprise the model matrix, okay? And 2 more runs. Now we only add 2 more runs to the original experiments. So this is table 5. This is a experimental design matrix, experimental matrix. You need to specify B, C, D, E, Q, the levels, and then you run experiments. And then at the same time, you add this block, BCQ, DEQ, DQ. Why do you add them? Because they are model matrix. You include them in your model, right? Now, so if we run 2 additional runs, how many options we have? So here we have how many options? You have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You have 10 options, 10 blanks to fill with minus plus, right? Then you have 2 power 10 opportunities, okay, for each cell, for this group of 10 cells. Now, if you define those plus minus signs over here, then plus minus sign automatically define over here because BCQ equals to BCQ multiplied together, and the block has already been defined. And we want to choose the signs here so that you see here. So we have about 2 power 10 possible choice of factor settings follow-up runs, run 17 and 18. Now, and each factor can take either plus or minus levels. For each of the 1024 choices for run 17 and 18, we denote the corresponding model matrix XD, okay? So for each choice, you can have XD, model matrix. And what we want to do is we want to choose the factor setting, D star, okay? We want to maximize the D criteria. That is maximize the D criteria, minimizing the volume of the confidence ellipsoid for all model parameters beta. Okay, so we want to, because when you do the linear regression, it's X transpose X inverse, then X transpose Y, right? So what we want to do is we want to maximize this one, the design matrix, and then the factor settings, the X, the model matrix. So this is our model matrix, okay? So that we get the maximum D criteria. Now, if you want to maximize this, and you will be able to get these settings, then you put these settings, D1, D2. Both of them get the same maximum values. So you get these 2, and then you put it in, and those will be the 2 follow-up runs. However, we may primarily be interested in the BCQ and DEQ. Then the XD may be and XD transpose X will be partitioned into submodular matrix, submatrices. So this part X2 will corresponding to BCQ DEQ only. Then instead of this matrix maximize it, we are trying to maximize the lower right 2x2 submatrices inverse, can be shown as this, okay? Then the optimal choice of D is one satisfies this criteria. This is called submatrix optimal criteria. S denotes the subset. Then if we use this DS criteria, then the lower right will have the value 1 to 8. And on the other hand, the DS criteria for D2 is 113. So D1 is much better than the D2, so we use D1. So those are the follow-up designs, or you can call it sequential designs. They have different criteria. You can also use the design tables, because in the book we mentioned in the first slide, they put those fractional design, the best fractional design, they have already been identified in the appendix. And the minimal aberration design are given in the table. So if you want to do the experiments, you can just take those designs If two designs are given for the same K and P, the first is the minimal aberration, the second is better in having the large number of clear effects. Okay, those are the two example tables. So in table 7, that is the first 2 power 9 minus 4 design. Table 7, this is 6, this is 7. Okay, now first let's have a look at table 6, because this is the first bullet, right? And then we're going to talk about table 7. Table 6, how to use the table. For example, you have 5 factors, but you want to do the half of the design, fractional design. So, and this is the best design. So you do the 1, 2, 3, 4, 4 factorial, and then 5 equals to 1, 2, 3. This is a generator. If you have 6 factors, this resolution will be 4, will be 5, this will be 4. So you do 1, 2, 3, 4, 4 factorial design, then 5 equals to 1, 2, 3, 6 equals to 1, 2, 4. The same for all others. And then all the clear effects are given. You can see all these designs. So in table 7, the first has minimal aberration and 8 clear. The second has the second best according to the minimal aberration, but has more clear effects. Okay, let's see. 9 minus 4. You see here, we have 2 designs for K. If you K is the number of factors, and F and R are fraction and resolution. So number of factors we have is 9. 2 power 9 minus 4, that means we only want to do a small fraction. And then we are going to do the 1, 2, 3, 4, 5, 4 factorial, 2 power 5, 4 factorial. And then 6 equals to, 7 equals to, 8 equals to. Those are the design generators. That means you don't need to specify the level of 6. They just equals to 1, 2, 3. And you can see that the first design has 9 main effects, but has less 2-factor interaction clear effects than this one. So that's why both of them are given. So it's not it's common that to find a design with slightly worse aberration but more clear effects. Thus, the number of clear effects should be used as a supplement criteria to the minimal aberration criteria. Now, choice of the fraction and avoidance of specific combinations. For example, you do the 2 power K minus P design has 2 P choices. In general, using randomization to just use one of them. But if you use 2 power 7 minus 3 designs, you can have 8 choices, okay? 2 power 3, 8 choices, because 4 equals to 1, 2 up. You can randomly plus and minus signs over here. But some of the specific combinations, maybe plus 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 is high pressure, high temperature, and higher concentration. They may be undesirable, maybe not safe enough, right? So you can avoid them by choosing different kind of random designs. So in addition to the fractional design, we can also use blocking in the fractional factorial design. For example, you can have 2 power 6 minus 2 design in 4 blocks. So this is a design defining contrast subgroups. So 5 equals to 1, 2, 3, 6 equals to 1, 2, 3, 4. No, 6 equals to 1, 2, 4. So, but at the same time, you can choose a block. And you can arrange them into 2 blocks, okay? Not 2 blocks. You have 2 block relationships. That means you can have 2 power 4 blocks. That means 4 blocks. And then you can derive the confounding relationship, because confounding is blocks. And you can also get the aliasing among those factors. And however, in the book has already give you the design tables for blocking. Among the 15 degree of freedoms for the block design on page 33, 3 are allocated for block effects, 6 are for clear main effects. The remaining 6 degree of freedom are 6 pairs of Alias 2-factor interactions. So for the same 2 power 6 minus 2 design, if we use the block generators like this, there's a total of 9 clear effects. Those are the 9. Thus, the total number of clear effects for this block design is 3. More than the total number of clear effects for the block design on page 33. However, only main effects 3 and 4, 6 are clear. So what are they referring to? Because they are trying to show us table 8. Table 8 is right here. So this K, what is a K? K is the number of factors you have, okay? And what is a P? P is K minus P is a fraction, 2 minus P fraction of the design. And the Q is the number of, 2Q is the number of blocks. So for this one, you have 5 factors. You only want to run 2 minus P, 2 minus 1, that means 1/2 of the design. And then you have 2 power 5, that is 32, 1/2 of it. You only want to run 16 runs. And then you want to arrange the 16 runs into 2 blocks, 2 power 1, right? 2 blocks. So the design generator is 2 power 4, 16 runs, and then 5 equals to 1, 2, 3, 4. And then the block will be B1 equals to 1, 2. And those are the best designs that are given for different combinations. You see here, different combinations. And they were given in the appendix. So if you want to use some of the design, you can directly use them because they have already been evaluated and validated to have based on the minimal aberration criteria and also the large number of clear effects. So all the clear effects are given here. And the same here. These are you have 7 factors or 8 factors or 9 factors. You can just pick the corresponding designs and also the block arrangement. Why do we need a block? Because you cannot really, sometimes you cannot finish all the experiments in one day. You want to allocate them into 2 days or different days. So that means you have different blocks to do the experiments. So more fractional factorial design in blocks can be are given in the book. WH means Jeff Wu and Hamada book. You only need to learn how to use the tables and interpret the results. Theory or criteria used in choosing the design are not required. If you want to just use it, you can go to the appendix and use them. But those theory and criteria we discussed in today's class. So this is the end of the fractional factorial design. Hope you have learned how to run half of the experiments or maybe a fraction, 2 minus P fraction of the full factorial design. This will be more economic, okay? Economic, instead of spending a lot of fund on the full factorial design. You can do a fractional design and then you add the follow-up designs and the follow-up experiments. Okay, this is the end of this lecture.